type in the chat right now.
All right, and
Just
then
type in the chat right now. I don't have the polls yet.
oh, a lot of people like the snack. That's funny. Only a couple people like Monty Python. You guys, Monty Python needs to get more love, guys. Snack is super superior. That's definitely the truth. Um, Ishan, if you get a chance, actually, if you don't mind making the second poll, if you get if it's not too difficult to do, because that's something that
I
will.
think maybe the person who created the meeting has to make the poll. I'm not
Yeah,
sure.
I don't think we can do it actually, which is why I was unsure.
Oh, well, that's okay. We'll have people respond in the chat then for next time for another poll that's a little bit more serious coming up. So, Holy Grail is one of the best movies, but true, however, Sneck, yes. Um, I don't know. What do you guys think? Is the Sneck thing? Is that an ancient meme now? Is that long gone? I don't think I've seen Sneck in a while.
People still, I don't know, people still say like that kind of stuff,
Yeah. No, bro. But anyways, all right. So let's get started. So we're going to so this is a Qiskit workshop. Qiskit, we'll talk a little bit more about what Qiskit is. Qiskit is a Python library, basically a programming framework that is used to program quantum computers. So starting out, we're going to actually talk about what quantum computing is. If you guys have been to our other workshops, you might have seen a little bit about like what quantum computing can do. This time, we're actually going to talk a little bit more about what quantum computing actually is and how to do actual operations on a quantum computer. It'll get a little bit more in depth because there's some prerequisite knowledge that you guys need to know. We'll try and keep it nice and simple, but for those of you that have seen a little bit of linear algebra, that's definitely going to help you guys out. Maybe some vector calculus that's going to help you guys out. But if you haven't, I think that at least the very basic building blocks of this stuff, I think you'll also be able to understand. So I would say, stick with it. We'll go over it very briefly and just try and understand as much as you can. So first of all, we're just going to do a general overview. The type of computing that you guys are used to, we call classical computing in the field of quantum computing. Someone asked how long the workshop will be. We're going to try and end it around like 4:50 or so, a little bit before 5, and we'll do a Q&A at the end. So it should be another 40 minutes or so. But who knows? We might go a little bit over, knowing us. So classical computing is the type of computing that you guys are all used to, right? And classical computing uses what we call classical bits. So it uses zeros and ones, right? So classical computing, you can either be in a 0 state or a 1 state, right? And just like classical computing, in quantum computing, we're not going to worry about what the hardware is, right? So when you're, even if you're programming an assembler, for example, or something like that, some really, really, really low level thing where you're actually dealing with binary, you're still probably not dealing with like stuff on the level of, how is a charge being stored? Are you using MOS capacitors? Are you using, some other hardware? Are you using optical computing, whatever, right? We're not worrying about that too much. Same thing with quantum computing, right? But yeah, so classical computing, we got zeros and ones. Quantum computing, we have something called a qubit, which is our quantum analog of a classical bit, a 0 or 1. And a qubit is basically just a mathematical object. We'll go over a little bit about what it is exactly, but just a mathematical object that has certain properties. And some of these properties include superposition, entanglement, which we probably won't talk too much about those properties as much. But if you keep attending our events and stuff, we'll really inform you guys about what those are. And the promise of quantum computing is we can have faster search algorithms. We can have faster prime factoring. Those are two of the kind of the big. We talk about Grover's algorithm and Shor's algorithm. Those are two algorithms that are used a lot, that are kind of big buzzwords in quantum computing because they could be used to speed up searching and to speed up prime factoring. So let me clear this. So we're, come on, there we go. So this is kind of, this is all we'll talk about what quantum computing can do. But I think this is a really good kind of starting off point to understand why this, why one should even learn Qiskit, right? It could, you know, if quantum computing does wind up taking off, if this technology winds up being built and we have big giant quantum computers that can are much more powerful than the ones we have now and can do these really complex tasks, these are some of the tasks that one could do with a quantum computer. So we talked a little bit about RSA encryption in our last workshop. Basically, there's an algorithm called Shor's algorithm that could allow quantum computers to factor giant numbers a lot faster than a regular computer can. In fact, it has what we call an exponential speedup. So as you add a digit to a number, right, the complexity of factoring that number goes up exponentially, right? If you add one digit, you have to check 10 more numbers. Quantum computer could use these quantum phenomena, something called Shor's algorithm, to be able to factor those numbers in polynomial time. So that speed up is, instead of being exponential, instead of going super, super sharp, we kind of have a polynomial speed up, or a polynomial complexity, which is very exciting. We talked about a little bit about that in the last workshop as well. So I'll kind of glance over some of this stuff. There's also quantum chemistry. So these orbital simulations, right? Chemistry is just electron interactions. The interactions of these electron orbitals, those problems become really, really, really complex really fast. And those are physically quantum systems, right? Electrons are quantum particles. They have quantum properties. And so using quantum computing to simulate those lets us do that a little bit faster and has a potentially exponential speed up as well on that one. The eventual kind of dream of quantum chemistry is the ability for anyone to be able to do chemistry experiments and simulations without having to, you know, build a super complex algorithm or having to, you know, go into a lab and synthesize a chemical. So that's really exciting. We'll see if that winds up happening. And then finally, we're dealing with end-to-end encryption. So that's something that quantum cryptography could be responsible for. We actually partnered with ACM, and Ishan directed a workshop on quantum cryptography in the winter quarter. So let's see. I might have to go here. I'm gonna paste this link for you guys so you guys can check that workshop out. That was a really cool workshop. I think you guys will really enjoy it. So yeah, check that out if you get the chance. That goes over a lot of more stuff about quantum cryptography. And the idea is you can have perfectly secure encryption with this type of cryptography, which is really exciting. So that's just a brief overview of kind of what we talked about in our intro workshop about the applications of this technology. Then we're just going to go over a brief overview of what we're talking about. We're going to try and cover quantum computing enough that you need for this workshop in about 10 minutes or so. We're going to give you a little crash course on Python very briefly, and then we're going to go over Qiskit and what you can do with it. So it's going to get really, really interesting stuff. And then finally, at the end, we're going to have like a little question and answer, let you guys ask some questions about anything that you so choose. So yeah, I'm going to go over a little bit of what quantum computing is, what the actual physics is behind it, and the math behind it. So if you guys were kind of curious about this stuff but didn't get the chance to really see an explanation of this previously, this would be maybe a good chance for you guys to check this out. So we talk about a qubit, right? So a classical bit, which is just a bit in a computer, a 1 or a 0, right? That's basically, my understanding is generally that's stored as a charge in a tiny, tiny, tiny capacitor. So you have a tiny little capacitor, and you either have, you either have some charge Q here, right? Whoops, come on. Or you have a charge of 0, right? That's your physical representation of a bit. But we're not even really too worried about that physical implementation, right? That physical implementation could be anything. You know, people have designed computers that work on various different hardware platforms, and they work perfectly fine, right? We have optical computers. People have made computers with light. There's people have made pneumatic computers, right? Different types of computing platforms that work perfectly fine. So a qubit is very much similar to that, right? You can use different physical systems, for example, the spin of an electron, um, and specifically, just like a classical qubit is any system that can be in two different states, right, a 0 or 1, right? A quantum bit or a qubit is any physical system that can be in the in two different quantum states. So I think a nice little example that we like to bring up is Schrodinger's cat, right? So remember we have Schrodinger's cat. We have a box, and then we have a isotope, right? And that isotope can decay and give off an alpha particle. And that isotope has some probability, let's say a 50-50 chance of decaying in that 5 minutes that we leave that thing in the box. If that does give off that alpha particle, right? We have a little cat in this box, and that cat will, make sure I draw my cat. There we go. So that cat will, let's say, will release a painless sleeping gas into that box, and that cat will fall asleep. Okay, so we're not going to kill the cat. If that alpha particle is given off, right? And the idea behind quantum computing, behind a qubit, is that until we open that box, when we leave that box closed, that physical system exists in what we call a superposition. So you guys might have heard, the cat is both dead and alive, right? That's essentially what a superposition is, right? This physical state of that system is some combination of dead and alive, right? And any quantum system, for example, the emission of an alpha particle in a radioactive decay, or the spin of an electron. The spin of an electron can either be up or it can be down. It can be positive h bar over 2 or negative h bar over 2, right? Don't worry about what spin even means, but again, we're just dealing with a system that can be in two possible states, and we can actually have electrons that are in superpositions or that are not quite in one or the other spin state, right? Same thing with this polarization of a photon. So we can have, a photon where the electric field points up and down. We can have a photon where the electric field points, horizontally, and we can have a photon that exists in some superposition, some diagonal polarization, right? Same with the energy level of electrons. The electron energy levels is what IonQ, if you guys have heard of IonQ or Honeywell, are using for their quantum computers. We also have a bunch of exotic physical phenomena. So people have done, neutral atoms, ultra cold neutral atoms, Bose-Einstein condensates. People want to, what I think Google and IBM are using is something called superconducting Josephson junctions. So that's something that I don't even fully understand. But the idea is, any realization you want to use is essentially the same. The math behind it is exactly the same. So let's talk about what a qubit is. So a qubit is basically a vector. So just as you guys, and if you've taken either linear algebra or even like vector calculus, this might be a little bit easier to understand, but even if you haven't, I think you guys will be able to at least grasp this basic kind of concept. So we have something called basis vectors, right? So let's say we have some vector in 2D space, right? So this is just 2D space, and here's some vector, and I think I could, let's draw it over here, like that. So we have some vector v in our 2D space, right? That vector v can be decomposed, we say. It can be, we can figure out what it's composed of. So we have, this basis vector, this is called a basis vector, this is called I hat. So you guys might have seen I hat before, right, from your some of your math classes. Or we have this thing right here. This is called j hat right here. So we can say this vector v is, so we can either represent it, like this. We can say, okay, this looks like maybe like what, 2, 1 right here. We can also represent it as a column vector, which is, I think, what we'll be using today. So we can say 2, 1 like that, right? Just same thing, different representations, right? We can also represent it like this. We can say it's 2 times this vector 1, 0. So it's 2 times this vector. So it's like that, right? This is 2 times 1, 0, and plus 1 times the vector 0, 1 here. So this one right here is 0, 1. And that's just 1 times that, right? So really basic stuff, right? You've seen this stuff in your math class. The maybe a little bit trickier part is representing this in terms of these little basis vectors. We have 2 times I hat, where I hat is just this thing right here, right? Plus 1 times j hat, where j hat is just this thing, right? In quantum computing, we're using a very, very similar concept, except instead of using I hat and j hat, we're actually using these states. We're using the state 0 and the state 1, right? So that vector up above would be 2 times 0 plus 1 times 1 here. But again, same exact math, just a different way of representing it, right? Just, for whatever reason, they like to use this 0 and this 1. Those are basically, the 0 and the 1 state are basically the same as our classical 0 and 1, right? In our regular computer, we have our 0 and our 1 state, right? Jumping off of that, it gets a little bit more complicated because, in reality, a quantum state is a little bit more complicated than that. It also has something called a phase. So instead of just being, somewhere between 0 and 1, so we can have some vector here or here or here, we also have some we call complex phase, which we won't worry too much about. But just something to keep in mind that is a little bit more complicated than that. Let me just show you guys a representation of an actual quantum vector in something called the Bloch sphere. So let me just minimize this real quick and show you guys, I think it's this one right here. So this thing right here is, we call this the Bloch sphere. So this thing is, you guys might have seen this before if you've messed around with, maybe watched some videos on quantum computing. This thing can be, as we said, right, this vector up like this would be the 0 state right here, right? So let me just draw here. This is the 0 state up here, and then down here is the 1 state, right? And we can change the angle between these two states, and we can have this qubit go from the 0 state to when it's exactly in between, right? Then we have an equal superposition, or half and half state here, or it can go all the way down to the 1 state, right? So we're in the 1 state, we're in the half state, right? And we're in the 0 state. This specific qubit is using spins, electron spins. So when we're in this state, our probability of getting, so we'll talk a little bit about what the probabilities are. It's a Aaron's joke. Yeah, it's a Bloch sphere, as in the British bloke. Yeah, but the idea is, we can exist in some superposition, some kind of combination of the 0 and 1 state. And like the cat, right? We open the box, we're not going to see a half alive cat or a half asleep cat, right? We're going to see either a fully dead or passed out cat, right? Or we're going to see an alive cat, right? That's moving around. The same thing with this, right? If we actually measure this electron, we're never going to get this state, some arbitrary state here. We're never going to actually get, this value, this 0.655 or whatever, right? We're always going to get either a 1 or a 0. So, if this vector is closer to the 0 state here, then when we measure that this quantum state here, we're going to be much more likely to get the 0 state, right? And if we're closer to the 1 state over here, then we're much more likely to get that 1 state down here, right? So you can, I'll dump this link real quick in the chat. You guys can play around with this. It's kind of a fun little visualization. It gets a little more complicated because you also have something called a phase. So if I can go halfway, right? So I'm halfway right now. I can actually go all the way around this sphere as well. We're not going to worry about what that means because I'm not even sure I fully understand what the azimuthal angle is or the phase of a qubit is, right? So we're not going to worry about that too much, but just understand, it's a little bit more complicated. But I think for today, you guys can imagine a qubit as just something in between 0 and 1 that can take any range of values there, right? All right, so a lot of stuff. I'll pause for just a quick second and kind of let you guys let that sink in for a second. Give my voice a break as well, and we'll go on to the next slide. So we're almost there, almost ready to build our circuit. So we talked about measurement. We talked about we talked about probability of measurement. It's the magnitude squared of the amplitude. We're not going to worry too much about what that means. But basically, if I have, for those of you that have taken linear algebra, let's say I have alpha times 0 plus beta times 1, and these are just some numbers. And we can think about this without the phase. You just think about it like this. Let me draw that a little better. Whereas this is a vector of length 1, that's just somewhere between 1 and 0, right? Oops. Come on. This is 1 here, and this is 0 here, right? And that's represented by alpha and beta. The magnitude squared, so you take the magnitude of alpha and you square it, that's the probability of getting the 0 state. And then the magnitude of this beta here squared is the probability of getting the 1 state. So a little bit more advanced there. We're not going to worry too much about that because what we're going to do is we're just going to go all the way halfway, and then we can just go, okay, the probability is just 1/2, right? So that's what we're going to do. We're going to take a bunch of qubits, right? So these are all qubits. This is a circuit diagram for a quantum circuit. So real exciting stuff. We're going to take these qubits, and they're going to start out all in the 0 state, right? So we're going to be dealing with all 0 states. And then we're going to apply something called a Hadamard gate. We're not going to worry too much about what a Hadamard gate is. I originally planned on trying to explain it, but I think it's a little bit, it'll probably bog down the workshop just a little bit. But the idea is a Hadamard gate will take this 0 state to an equal superposition of 0 to 1 state. So it'll take it to the probability of getting 0 is going to be 1/2. And the probability of getting 1 is also going to be 1/2. Right? And we can, and we can look at that here. So if we take our Bloch sphere here and we put it into a halfway superposition there, right? We see that the probability, measurement outcome probabilities, right, are both 1/2, 0.5 here, right? So real simple, right? We won't worry for now what a Hadamard gate is. What it turns out, a Hadamard gate is actually a linear transformation. It's a matrix that we can multiply by that vector. And if you guys attend our future workshops, you can learn a little bit more about the linear algebra behind that. I think linear algebra is actually very, very elegant and a really cool way of thinking about this stuff. I think when you can get a really good intuition on it, I think the way they teach it a lot of times is not very unintuitive and computational, and makes it a little bit more tricky. But I've been trying to teach it. I taught some little study sessions over the summer. I think we got the linear algebra to not be as bad. But anyways, so we're gonna look at that circuit. So I'm gonna go to where am I? Here. So this is the IBM Quantum Composer, where I can actually build a circuit graphically here. So I can take, this is a H gate or a Hadamard gate. I can take that gate, I can drag it down here. So this qubit right here, before I do this, right, so I can delete this gate. before I do that, this qubit is in the 0 state, right? State 0, probability 1, right? Take this Hadamard gate, put it down here. Now I'm in a different state, right? My probability is now 0.5 of getting the 0 state and 0.5 of getting the 1 state, right? So that's pretty cool. I can actually build my quantum circuit. And then what I can do is I can actually do a measurement on this qubit. So I can measure this qubit, and now I'm going to get a 0. I can actually do it again, and I might get a different result the second time I do it. Or it might just automatically give me a 1 each time, or a 0 each time. Yeah, it's probably just giving me the same result, but that's okay. Yeah, so I do my measurement, and I get 1 result, right? So we can use this. Yeah, so that's the website right there. Yeah. So we can use this to create random numbers, right? So if I have equal superposition, I have this split state between 0 and 1, right? And I measure it. That means I get a random number, right? Is my problem? Same thing with the cat, right? The complete randomness determines whether or not that cat is going to be dead or alive, or passed out or active, right? So that's really exciting because yeah, we'll actually be going back and showing you the full implementation of this circuit on the near the end of the workshop on this circuit composer here. So yeah, I'll let you guys kind of sit on that for a second. I'll get the rest of the stuff queued up. We'll talk a little bit about Python. But I think that is everything I wanted to talk about. The last thing, I guess, is this kind of random number generator thing. So what I can do is so I'm generating a random 1-bit number, right? It's a bit of 1 or 0. I can actually generate a random 2-bit number, right? So now I'm either gonna, I'm gonna get a 0, 0, 0, 1, 1, 0, or 1, 1, and the probability of each of these is 1 and 2, right? So I can scale this up. We're actually going to see an implementation. We're going to use 8 bits to generate a random number between 0 and 255, and then we're going to normalize that and actually build a quantum random number generator. And keep in mind that a quantum random number generator is actually truly random. So your computer, when it generates a random number, when you run some random number generation software and some built-in function in C++ or Python or something, those numbers are actually going to be what we call pseudo-random. So we're going to use stuff like clock cycles and little errors in our in the architecture of our computer to generate those random numbers, and they're not going to be truly random. They're going to follow some distribution. And if you know that distribution, you can actually, break cryptography and do stuff like that. So having actual random number generators, quantum computers definitely not, it's not what quantum computers will be used for. It's not a very efficient use of them, but it's just a really good demonstration of how, if we actually use this random property of nature, the fact that when we measure this, we get a random number, we can actually get true randomness. So I think that's really cool. All right, so I'm going to take a little bit of a break, and I'm going to hand it off to Ishan. Wait, we're going to do here. And so here's our circuit, right? We have 8 qubits. We run a Hadamard gate on each of them, and then we measure each of them, and we get an 8-bit random number. So we're going to talk a little bit about Python, and Ishan is going to go through the Python that you guys are going to need for today.
Yeah, so actually Michael is going to be teaching the Python, but we do have this poll for you. We just want to gauge. Yeah, let's launch that one.
Oh, you actually have the poll. Awesome.
Yeah, Aaron was able to do this. He's actually a god.
Let's go.
My ITS powers.
Yeah, actually, that's literally how he has.
I went on the admin panel and then found the meeting, and then edited it there.
Yeah, I told you, Aaron's a god.
Oh, yeah, 17
Wait,
ones.
Guido van Rossum is here twice? Holy cow.
Wow. In the flesh, huh?
Oh my god, he must be disguised as one of these random names, you know?
Mm, that
And
makes
there's two of him.
sense.
Oh man.
Well, I got 18 responses. That's pretty cool. See if we get two more. It's all right if you guys don't answer it, but it might be cool if we can get everyone. Looks like the winning result is decently familiar, so that's good. So for those of you that are beginners, the 7 of you guys, you might want to pay attention for this one. That it'll help you out a little bit, I think, for understanding what we're gonna do next.
Okay, cool. So I'm gonna end poll now. So now, yeah, why don't I share results? Why not? Yeah. So uh, now Michael's gonna teach you guys what you need to know about Python for this workshop in particular.
All right, sorry, needed to make sure there wasn't going to be an echo. All right, so looks like everyone has at least seen what Python is a little bit before. So yeah, there's a big wall of text here. Don't worry about it. It's a lot of it's just extra information that you don't really need to know the details of. So yeah, so the first major thing you just need to know is just what that import statement is. So basically, all the code we're going to be using for Qiskit is going to be written by people at IBM who are a whole lot smarter than at least me. So all that stuff we're just going to import and use that import statement. So that'll just let you have their code, like their code for accessing everything all pulled onto your environment. And you'll see more details about that when we get to the coding section. So the other thing you need to be aware of is objects in Python. So in Python, objects are just a way to store certain stuff in a way that kind of makes sense for people. So when people make objects, they might make it, they might call it for some sort of abstraction. So for instance, in this case, you could represent a ball as an object and it has different traits and stuff. For Qiskit, I'm pretty sure we're going to do stuff like abstract a quantum computer. So it's like, hey, store this qubit as an object and it has certain traits on it. And so that's how we'll be kind of interacting with stuff when we're trying to code everything. Additionally, there's going to be functions. So objects will have different functions tied to it. So if you have a ball object, then you might have something called a role, which will be a function for it, and you'll do something with it. So to compare it to Qiskit, we might do something like add gate would be a function called on the quantum computer object. And that will be a way for us to talk about what we're doing using the code here. So there's more details, but that's generally what you need to know for Python. So I guess any questions about that? I kind of went through that fast because everyone seems to know something about Python, but if there's questions, like please do ask. Well, there is no questions. So, all right. I guess I'll hand it back to you, Ben.
All right. Yeah. Thanks, Michael. Hopefully that um, hopefully that answers or gives you guys a little bit of a background on Python. Um, so we're gonna now go on to talking about what Qiskit is, and we're let's see, it's about 4:41 right now, so we're gonna try and end this thing at 5. Might be about 5:10, 5:15 if we wind up going too slow. So I might glance over a couple of these things. Qiskit basically is a programming language or a Python library, technically, that can be used for quantum computing. It was released in 2007 by IBM, and it seems like it's become the de facto default for quantum computing. Everyone seems to be using Qiskit nowadays. And so I showed you guys this. This is the circuit visualizer that we used earlier. And they partner with different hardware platforms to try and deliver, some sort of universal quantum computing access. So that's really cool. And so we're just going to talk about what a Qiskit program does. First you're going to build the program. So you're going to, design your circuit. So the way that I drag those things, right, we're going to do that using code this time. Then you're going to compile your circuit. So you're going to turn it into an object that the Qiskit kind of architecture can handle. You're going to run that. And that's going to either on a simulator or on an actual quantum computer. We're going to talk at the end about how to run it on an actual quantum computer. And then finally, you're going to analyze your results, right? You're going to get some distribution, right? You're going to run it a certain amount of times, and you're going to get, some result, some amount of each results, and you're going to analyze that and come up with your, determination that you make, right? Whoops. So this is the end for our presentation. So I'm going to go on to IBM's Quantum Lab. So this is something that you guys can actually check out and do alongside us. We originally kind of designed this workshop to be something that you guys can do at the same time as us. So I'm going to post this link here. If you guys don't mind, I would love it if you guys can go on this website and kind of go through the process of creating accounts here. We were originally going to do something called QBraid, but it turns out this might be a little bit simpler, and it'll get you plugged into IBM's ecosystem as well. And this is really nice. It's just plug and play. So I'm going to go through the account creation with you guys so that you guys can see how it's done. But feel free to just create your account on your own time. It shouldn't only take less than 5 minutes or so. And once we get all our accounts set up, hopefully you guys can join me as I kind of try and walk you through this stuff. So I'm going to create an IBM ID. I'm going to use the email for the Quantum Computing Club. So we're going to do, let's see, what is it? Quantum Club at ucsd.edu. And I'm going to use my name. And let's use, where is it? Get my password and United States, right? I'm going to verify my email with a 7-digit code. So that's going to be, let's see if I can find that. Right, so you guys can do this as well. You can type in your
The code is, I have it. Do you want to put it in?
Oh, I already got it. It's all
Okay.
good. Thanks, though. There we go. And create account. So that should work. You can proceed with their account privacy, right? So once they do that, and hopefully you guys can do this with me, because that would be really cool, because we're going to actually write the Python code in this quantum lab here, which would be really cool. So you got your end agreement, you got to accept that, right? I'm not worried about that for now.
Is anyone at this point still making the account?
All right, so I'm going to assume I use the Quantum Club email. So there we go. It's going to be starting up. Has anyone gotten past this screen and has gotten to their server? Let me know. Yes, awesome, cool. All right, so we all are in. So I just got to my server as well. Let me know if any of you guys have any issues with this, but otherwise, we're gonna go ahead and keep trucking on. So I'm going to. So you guys can join me and write this program with me if you want. I'm just waiting for this to boot up. So we're gonna all click on this first thing, the IPy kernel here. Just double click that. That's going to create an untitled notebook, right? And it's going to do a bunch of automatic imports. We're going to get rid of this stuff, and we're going to start from scratch. So here's what we're going to do. We're going to import Qiskit. Whoops. Okay. And then we're going to import some other stuff from Qiskit. And so that for example, we're going to import, and let me know if I make a mistake, if you see me do anything like misspell anything, right? Because when I practiced this, I made a couple spelling errors and had to redo some of it. So we're going to import quantum circuit and transpile. That's so that we don't have to do Qiskit dot, transpile. We can actually just use transpile by itself. We're not going to use those two for anything else, so we don't have to worry about polluted namespaces, if you guys know what that is. So from Qiskit, we're also going to import Qiskit.providers.aer, and we're going to import Chasm simulator from that. Oops. We're also going to import a visualization tool, and that's going to allow us to visualize our circuit, to do a little bit of a plot histogram like that. So you guys can you can join me on doing those imports, right? And then we're going to use the, okay, so there's our imports, right? So first of all, we're going to set up a simulator. So because we can't actually run this on a on an actual quantum computer, we're going to set up a simulator. That's going to use this method. Michael talked briefly about like what an object is and how to use methods of an object, right? This is called an initializer, or a it's an initializer function. So we're creating a Chasm simulator object, and we're naming that object simulator. So for those of you that are interested in the Python involved in that, then what we're going to do is we're going to create a circuit using a similar process. We're going to use the quantum circuit initializer, and we're going to initialize the quantum circuit. And we're going to have 8. So this 8 is going to be 8 qubits, as well as 8 classical bits that we're going to use for this circuit. So again, we have those. We're going to be dealing with 8-bit random numbers, right? So we're going to have 8 bits, and we're going to initialize all of those, and we're going to measure those. When we measure those, we have 8 classical bits, an 8-bit register that we use to store the result there, because they're going to turn into 0s or 1s, right? So that's what those 8s mean. Then what we're going to do is we're going to run each of these qubits through a Hadamard gate, right? Remember our original circuit over here, right? We have all these qubits, and we're going to run each of them through a Hadamard gate, right? And then we're going to measure each of them. So let's do that. So we're going to say for I in range 8, right? So we're going to go through 8 iterations, and we're going to just apply a Hadamard gate. So, as Michael said, we're going to use the .h method, right, of this circuit object, and that's going to run each of these qubits through a Hadamard gate. Then we're going to, and we could do this in the same loop, but we're going to do it in a new loop. We're going to measure each of those circuits or each of those qubits as well. So let's do that. What is it? Circuit.measure, right? Okay, yeah, there we go. Right, measure each of those qubits. Finally, we're going to compile our circuit. So we're not going to worry too much about what that means, but we're going to name this compiled circuit. Easy enough, right? And we're going to use this transpile function to compile our circuit, and we're going to use the simulator object that we created, this thing, which is a Chasm simulator. That's IBM's built-in simulator that you can use. We'll talk later about how we might be able to actually run this on a real quantum computer. Finally, we're going to create a job, and that's going to job is actually going to be the output of this function run that we're going to run the function run on our simulator, on our compiled circuit, using the simulator. I'm sorry. We're also going to give it a number of shots. So let's start out with 1. So we're just going to run it once for now, and we can change that number if we want. Finally, we're going to save our result. in, remember there's this job object that creates created, that is the result of our simulation. It also has other stuff stored in it, but we want just the result, so we're going to get the result from our job. Finally, we're gonna save that result into a dictionary, into a Python data object, right? We're gonna call that counts. So we're gonna say counts is result, and we're gonna use the get counts function. That get counts function is gonna give us our result as a Python object. And we're going to print that. And if I didn't make any mistakes, that should run. What did I do? Measure. Let's see. Circuit. Oh, I'm sorry. So I made a mistake here. So I'm actually, the way I have to do this is I have to measure the ith qubit, and then I have to store that qubit in the ith classical register. So I have to store that 1 or that 0 as a classical object. So let's see if that works now. There we go. So we printed our result here, and we get a 1 there. So that's our quantum circuit there. So I'll give you guys a second and see if you guys got the same result there. I'm also going to copy and paste this code into the chat if you guys need it. It's not going to be indented properly, so you might have to mess around with it to get it to work. But that should hopefully work for you guys. We'll also try and get this uploaded as like in some sort of Python format, or as like a Git or something, so you guys can access that. So we'll share the code with you guys later in a more accessible way. But there's that code. We'll pause for a second. If you guys have any questions, if anything's not working for you guys, I'll go over what the code's doing one more time. So this is for all of our, we created 8 qubits, and though those 8 qubits are each having a Hadamard gate applied to them. So they're starting out in that 0 state, right? Just like a regular bit in a 0 state, and then they're having a Hadamard gate applied to them, which is going to put them in not a 0 state or a 1 state, but this equal superposition here, right? So as you can see here, if we take, and let's just do 1. If we take a qubit and we apply this Hadamard gate, it's going to put it so that it has an equal probability of getting a 0 or a 1, right? See, you say the probability of the state 0 is 0.5, probability of state 1 is 0.5, right? So that's what that Hadamard gate is doing. We're applying that Hadamard gate to each of our qubits, right? And then what we're doing is we're measuring each of our qubits. So if we put a measurement here, now instead of existing in this superposition, now it only exists in 1 state, right? So it happens to be the 0 state in this case, but it could be a 0 or a 1, right? The probability is equal here. And the second, so that's what those loops are doing. Does that clear it up for you guys a little bit? Let you guys think about that for a second. Awesome. Everyone get it to work? So it's just printing the result from that. So it's printing the result we got. We got a 0, 1, 1, 1, 0, 1, 1, 0. So that's our 8-bit. We got 8 bits, right? So here we have 8 bits here, right? We have 8 qubits, and those are each going to give us a 0 or a 1, right? And this right here that it's printing is just our result, and it got that result 1 time. You can also increase the number of shots, and so let's increase this to 10. So now it's going to run this 10 times, and we get 10 8-bit random numbers. So let's try that. So now we get 10 results here, right? And we can keep increasing this until we start getting like repeats. So let me just, this was extremely impractical. It's going to look really ugly, but I'm just going to increase this to 100, and that's going to give us a bunch of different results. And so we get to the point where now, so actually, can someone tell me how many 8-bit numbers there are? See if one of you guys is a CS major or something and knows that. Yep, 200. So it's actually that's almost it. Well, yeah, 256. So we're from 0 to 255, right? So once we get to 100, that's kind of pretty close to 256. So we're actually getting some stuff twice, right? We're getting this number twice. This number is coming up 3 times, right? So that's kind of interesting. We could do it. We could even increase it more, and we'll get stuff coming up 4 or 5 times or whatever, right? So I'll let you guys sit on that for a second. It looks like we're probably going to end this thing at about 5 o'clock, but this is most of it. So if you guys, I think if some of you guys have to run to anything, you can head out now. But we're gonna just go through one more modification to this to turn these numbers into numbers between 0 and 1, so we can actually use this as like a practical random number generator. And then Ishan's going to show you guys how to run this thing on an actual quantum computer, which I think is really exciting. So real quick, before I turn it over to Ishan, I'm going to go over how to turn these qubits, these 8-bit numbers, I'm sorry, classical bits, I guess, 8-bit numbers into ones and zeros. So I have this function. I basically copy and pasted this function off of a Stack Overflow post. This turns our binary number to a decimal, and then it divides it by 255, right? So we have 256 numbers, can be from 0 to 255. We divide it by 255, we're going to get a number between 0 and 255, right? Or 0 and 1, I'm sorry. Does that make sense? We have numbers between 0 and 255. Divide them by 255, we get numbers between 0 and 1, right? I'll let you think about that for a second. So we're going to actually get our result as a number between, I'm going to turn it into a list that's going to let us access it and pass it into this binary to decimal function. Don't worry too much about what these are doing. We'll release the full code later with some nice and commented up and everything. But let's run this and see what we get as far as a random number. So now we're actually getting random numbers between 0 and 1, just like a normal random number generator would do on like a regular computer, right? If you ran random, like a NumPy random or something like that, it would give you similar results. We got 0.376, and we can actually confirm that that's the right number, right? So we can take this number, we can convert it to a decimal number, and then we can divide that by 255, and we get 0.376, and that should have been what we got, right? Oops. 0.376, there we go, right? So we're getting an actual randomly generated number. That's real cool. Yeah, so you guys are now certified quantum mechanics. You can go out into the world and do PhD research in quantum mechanics. All right. So that's it for our little random number generator function. So as kind of a last thing, Ishan's going to show you guys how to actually run this thing on a real quantum computer. And then after that, I'll let you guys kind of sit and think about this stuff and ask some questions if you got them. We'll do a little Q&A at the end. So
Okay.
go ahead and Ishan, I'll stop my screen share so you can share your screen.
Yeah, so as you probably saw, that was what Ben was running was like a simulation of a quantum computer. IBM, this IBM accounts that you just created has the capability for you to be able to run a program on an actual quantum computer, and I'm going to show you how to do that. So, okay, let's share the right screen. That's the one. This over here is the home page of the IBM Quantum site. You can just go to dashboard there, it's right there. And if you want to follow along, what you want to do, you want to go to Launch Composer over here. This is a very nice visual way of making quantum circuits. And then whatever you put over here, it'll also, you can also see it in Qiskit or even in QASM over there on the right. But basically, let's just, let's make what Ben made earlier, a random number generator. What it is basically was Hadamard gates on these 3 qubits. Yeah, so how this works is on the left over here, you can see there are 3 qubits. You can add more or remove some of them, but I'm just going to keep it 3 for now. So you put Hadamard gates to put them into a superposition. Then you want to measure them. This little icon over there with the Z in the top right, that is the measurement thing. So we're just going to measure all 3 of those, right? Now what this is going to do is it's going to give us a random number between 0, 0, 0 and 1, 1, 1 in binary. And you can actually, in the top right over here, you see this visualization seed. That is another way to to simulate this. So if you choose another seed, then you should, get another pseudo randomly generated result. You can keep doing that, but you can also run this on an actual quantum computer. So before I do, let's just name this random number generator. Okay. And then in the top right, you're going to see setup and run. Click that. Now you can select on the right over here, you can select the number of times you want that program, that circuit to run. So I'm just going to do 100. And so it's going to run that circuit to generate a random number 100 times. And you'll see after I run it, it'll generate a nice histogram of all of the results. We can name our job. So let's name it random number. And then on this left side over here, you can see a bunch of quantum computers that we can choose to run it on. You can see that there's a queue on each one of them. So like this one has 322 items in the queue. So we probably don't want to use that one because that'll take forever. This one looks like it has 0. It's at the top. I'm kind of surprised there's 0, but let's just grab it then and hope it works. So on the left here, we can view the status of our, oh, okay, it's running, good. If there was anything in the queue, it would say we are in the queue already. And yeah, it's done. It ran all of it. And now here's the histogram. We got 0, 0, 0 with a frequency of 28 and, so on and so forth. And that was run on an actual quantum computer, which is pretty cool.
That's cool stuff. I was gonna ask, how do you visualize the circuit? So hopefully Ishan answered your question about like visualizing this stuff. I think checking out IBM's kind of tutorial on Qiskit. So let me send you guys that real quick. So that you guys can go through that, peruse that on your own time. So yeah, interesting that we got a kind of weird distribution. Part of that is because quantum computers themselves are not perfect, right? They have all these errors, and especially the ones that they're putting that they're making available online are probably not like the most, their best quantum computers, for example, right? So that's probably why we're getting that distribution there. But yeah, it's really interesting. This is their website where you can learn more about quantum computing and Qiskit. Any questions you guys have about like visualizing circuits and what I just did in this workshop, hopefully you can check out some of their getting started material, and that'll help you. They have this nifty little thing. It asks you how much time you want to spend learning. It has any 1 minute, 1 day, 1 week, right? And it gives you a bunch of stuff, a bunch of resources for that. They have an introduction course, a Qiskit tutorial, a bunch of stuff like that. So I would recommend you guys, if you guys are interested in this is a great way to get started. So finally, also, we're gonna do a little Q&A. We have it on the, I guess I can, we'll keep Ishan's screen up there because it would have just said Q&A on our on our.
Yeah. If people are still there, I just ran it again, and we got a bit of a different distribution. So
that's kind of cool, right? So if you guys have any questions, feel free to ask, and I'll try and answer them as well as we can. Real quick, if you guys want to give us a little bit of feedback on this event, we have a little feedback form for you guys. If you guys are okay with filling that out, it really helps us understand what we're doing well, what we're doing not as well, and give you guys a little bit of a maybe better event next time, more tailored to what you guys are interested in. So feel free to fill that out if you get a chance. But yeah, if you guys have any questions, otherwise I'll see you guys. Hopefully we'll be able to have in-person events coming up pretty soon, and we'll be able to see you guys in person. So yeah, thanks for coming. Yeah, you're welcome, Quinn. Glad you enjoyed this. That's awesome.
Yeah, so any questions?
That's good. That means our presentation was perfect. No one had any
Yes,
questions.
we were perfect.
I know it's a lot of stuff, and I understand, some of you guys might be a little bit overwhelmed, but yeah, no, you're welcome, Joseph. Yeah, thanks for coming. Awesome to see so many people here. Yeah, crazy. You can run stuff on an actual quantum computer. It's pretty mind blowing. I'm not gonna lie.
Yeah. Earlier today, this computer Bogota wasn't working, so
Yeah.
something's wrong with it, but
Well, seems
we'll
like
probably fix it at some point.
yeah. Well, anyways, I'm gonna turn the recording off, and we're just gonna hang out. So if you guys wanna hang out with us, we'll probably just talk about this event and how we think we did. So you feel free to stay. But if you guys wanna head out, we'll see you later, and hope you guys enjoy your weekend and have a good one. You stay afloat in your classes too, right? All right. Take care, everyone. Stop the